Okay, class, in this video, I'm going to start talking about the second half of module number 1, which is, as you know, is chapter 2, all about limits. We have introduced the definition of limits. Now you have an heuristic idea of what the limit is all about. We made the calculation of some limits, and hopefully you start working with your exercise from homework 1 about the portion of the first half of the chapter number 2, which is sections 2.1, 2.2, and 2.3. Okay, now what we are going to start covering during the rest of these days is the second half of this chapter, that basically is how to evaluate two types of limits. One limits that is infinite limits, and other limits that is how is the behavior when the independent variable becomes larger, larger, and larger. What is going to be the behavior of the function? And based on that, we are going to use those concepts to evaluate some limits and also to introduce continuity. Okay, so let's start with this example that I show here in the lecture. In the lectures, we have this function, which is a rational function that you can see is the ratio of two polynomials. The numerator, which is a monomial, that is x, the degree is 1. And in the denominator, we have a quadratic function that is a trinomial square. And they say, okay, let's take a look of the limits of this function when we are around two numbers. The first one is -1, and the second one is 3. Okay, so the point is that these two numbers are not any two numbers, are very special two numbers. If you look here, this denominator, as I told you, we have a quadratic function that is s squared minus 2s minus 3, okay, and everything is square. Of course, if you solve this square, at the end, we're going to have a polynomial in which the degree is going to be 4. But let's concentrate here in this part, only in this quadratic function. Well, the point is that -1 and 3 are the two zeros of this quadratic function. In other words, when if I evaluate this trinomial in -1 and 3, the value of this trinomial is going to be equals to 0. So what is going to happen, I'm going to have a ratio that is indeterminate. It's going to be a number divided by 0. Now, a number divided by 0, what is telling to you is that we are getting a very large number in magnitude, either positive or negative. If I use a graphing tool, for instance, Desmos, and actually I encourage you guys to go ahead and open the application of Desmos graphics, okay, and plot this function in the way as has been done here. And you're gonna see that you're gonna get something similar to this one. You can see that whenever we are approaching in the independent variable, the number -1 from either side, it might be either from the left or from the right, okay, the function is going to be negative. But it's going to be negative in which way? That whenever we approach -1, where we're going to start getting very large negative numbers. In other words, we are going to have anytime very and very large numbers in magnitude, but in this case are going to be negative. So the function goes to infinity, but with negative values. Okay, so basically what this is telling to us is that really the limit of the function a -1 doesn't exist. Either, well, first of all, the function is not defined there, and secondly, it doesn't exist because anytime we are getting larger and larger negative numbers as we are getting close to -1. In that case, from the mathematical point of view, we say that the limit of this rational function when x approach the value of -1 is equal to -infinity. Now, this is a mathematical notation, okay? I don't want you guys to get confused. Really, the limit doesn't exist because anytime that I'm getting close to -1, I'm gonna get a larger number that is negative, and a larger number and a larger number. So it's not going to be steady to some specific number, as we saw in the first parts of this course, of this chapter. Okay, so it's always getting larger, larger, and larger. But from the mathematical point of view, to state that, we say that the limit is equal to -infinity. The same thing when we approach 3. If we approach 3 from either side, either from the right or from the left, okay, the values of the functions are going to be anytime very large positive number. So whenever I'm getting closer to 3, the value of the function is going to get higher and higher and higher and higher in positive number. So we say that the limit of the function when x approach 3 is going to be equals to infinity. Again, I don't want you to get confused. The limit doesn't exist. But because the function is getting larger and larger anytime, we say that is positive infinity. Okay? So, well, this type of things drive us to this definition. Okay? That is called, those type of limits are called infinite limits. And this definition is the one that you're going to find in your textbook. Okay? If we have a function that grows in a very arbitrary way with very large number whenever we approach in the independent variable some specific number, we say that that limit is infinite. If the function becomes negative and anytime in magnitude larger and larger and larger, but it's going to be negative, then we say that the limit is going to be -infinity. But again, here, in both cases, the limit does not exist. I want you guys to keep that in mind. This is only a notation. This is not a number. This is not a real number. Neither this one. It's a symbol that is telling to you that anytime in that limit, the function is going to be larger, larger, and larger. Okay? Perfect. Well, this is the definition for infinite limits. Now, what is the implication of that? So you can see here that this line, okay, if you want to express this line at x equals to -1, that is going to be a line. Okay? Let me go here. that is going to be a line, and these two lines are going to be vertical asymptotes for this particular function. So whenever you have rational functions, what you're going to do is look at the denominator and look or try to check when the denominator is equal to 0, because in those particular points, the rational function is not going to be defined. So those are the ones, those are the candidates that is going to tell you that probably in there, the function is going to go to infinity when we approach those zeros of the denominator. And the value of x at those points is going to give you the vertical asymptotes of the function. Okay, perfect. Now, let's go to this specific case. Okay, this is an example that I took from the exercise in your textbook. Let's consider this rational function that is 1 over x minus s squared. Okay, as you can see here, it's very, very easy to find out that we have two zeros. This is a quadratic function. One zero is going to be x equal to 0, and the other 0 is going to be x equals to 1. Okay, so what is going to happen around those two values? Well, in this particular case, you can see that if you approach 0, now from the right, the function is going to go and grows in a positive way. What is the meaning of growing in a positive way? That anytime I'm going to get larger and larger positive numbers. But if I approach 0 from the left, then the function is going to grow in the negative way. So anytime I'm going to have larger and larger numbers in magnitudes, but in the negative sense. So this limit in 0 is going to have one interpretation depending of from what side I'm going to approach the number. So the limit of the function when I go to 0 from the right is going to be infinitive, and the limit of the function when I approach 0 from the left is going to be negative infinity. In that case, we say that this is one-side infinite limits. Why is an infinite limit? Because the function grows in a very random way or arbitrary way, okay? But from one side grows in the positive real numbers direction, and in the other side goes in the negative real numbers direction. Okay, that is the behavior around 0. What is going to happen when x approach 1? Okay, so here is the function. Again, I use Desmos. Okay, Desmos is a very good application. I encourage you guys to download the application from the website. Okay, just you need to put Desmos in your browser, and that is going to bring the application. Okay, and we're going to use that one a lot during this course because that is going to give you a graphical representation in the function, and in that way you're going to receive some additional help to make the analysis of these limits. What is going to happen when I approach 1 from the left and 1 from the right? Well, you see here the branch of the function. At any case, you can see here that the function around this number is growing in one direction and in another direction in a very arbitrary way as I approach this number 1, but goes in different directions. So we are talking of an infinite limit, but that is different depending of from which side I'm going to approach the number. So I'm going to leave that to you to say here what is the behavior, and to say here what is the behavior with the corresponding symbol that I just showed you a few minutes ago. Okay, now, so we can see here that the function is now defined neither at 0 nor in 1. So x equals 0 and x equals 1 are linear vertical functions that are going to be now the vertical asymptotes. We can see here that at the infinite, when x is very large, the function goes to the x-axis. Well, that is another one that we're going to discuss on section 2.5. Okay? Which is the next section, limits and infinity. Okay? Thank you.